Okay, hello everyone. Thank you all for having me here. My name is Ondřej Uhlík. I am a PhD student at Faculty of Civil Engineering here at Brno University of Technology. And let me introduce you, I would say, first steps in our research at our department that deals with calibration of pedestrian ingress model in vaccination center or other facilities with high capacity. At the beginning, I can say, as you all know, that COVID-19 showed that engineers, organizers, and facility managers of high-capacity facilities need to focus more on optimizing operations of their facilities. So we believe that agent-based modeling, Pathfinder, and other tools can be a suitable techniques for these optimizations. And what we basically did and what I want to present is that we recorded a video recording of vaccination center waiting room operation, and we tried to extract some key parameters that we can directly put in Pathfinder or other agent-based model. So purpose of this work is to evaluate impact of these parameters that we extracted and to see some first results of our research activity. So what you can see in the left picture that raw trajectories that we got from external private company, they provided to us 400 smoothed trajectories from video recording that has 30 minutes. It's from vaccination center waiting room here in Brno from 2021, and it was recorded at 7 a.m. So the vaccination center just opened, so vaccination center clients didn't use seats, they just passed through the waiting room, and after we got these trajectories, we need to do some pre-processing techniques to filter and clean these data. So we used random forest classifier to detect false points caused by occlusion of camera. So, for example, when one person stands behind the other and camera didn't have a clear view on this person, the computer vision detector produces some false points, and we wanted to have an automatic approach to detect these points and remove them. And after that, we needed filtration that separated for us trajectories that belonged to vaccination center clients and to personnel, because we wanted to work only with clients' trajectories. But different paper will be devoted to these machine learning techniques that we used. So I will just leave it as I said. And after that, we need to do some perspective transformation. In other words, we had to transform 3D pixel coordinates to two-dimensional coordinates with metric system units. So picture in the right shows trajectories that we worked with for parameter extraction. So at the beginning of this phase, we needed to identify parameters that we want to extract, and some of them were more behavioral and one of them was physical. So behavioral parameters were about waiting, so waiting points extraction. I mean by that, waiting points location extraction was our first task. So at the beginning of this process, we needed to separate points of trajectories that we classify as waiting and walking. So waiting points that we classify as waiting need to satisfy two conditions. First of them was that instantaneous walking speed is less than 0.4 meters per second. And second one is that distance from position 1 second ago is less than 0.4 meter. And when we performed this separation, we wanted to separate those waiting points into clusters, because we believe that clusters are something that is easily implemented in agent-based modeling which we will see later. So second step was to perform two-dimensional Gaussian kernel density estimation to estimate number of clusters. So my colleague estimated that 4 clusters is optimal for this task, and after that we performed K-means clustering algorithm to determine a particular cluster for each waiting point. So picture in the right shows all waiting points separated into those clusters. And after that we computed geometric center for every cluster, and then we could implement those waiting points into Pathfinder, which we will see later. Second step was waiting time extraction. So we needed to separate or compute how many occupants or client centers just walk through the waiting room and how many of them waited or stopped once or twice during their walk. So 63% of occupants stopped once or twice in waiting room, and 37 of them just walk through the waiting room without stopping. So these 3 histograms shows distribution of those waiting times. You can see that those waiting times are very low because the analysis is very microscopic and they didn't have any reasons to stop, so the stoppage times are very low. So the histogram on the left shows waiting times for those who just stopped once, and the other ones shows first stop and second stop of those occupants who stopped twice. Input flow extraction. We needed to extract exact time of entrance for every occupant who entered waiting room. So based on these 2 graphs, we generated a step function that is also very easily implemented in Pathfinder. So every agent that enter the waiting room in simulation corresponds to exact time in video footage. And the last parameter that we extracted is physical, and it is walking speed. So we computed average walking speed for every occupant based on travel distance and time. And for model, we approximated this data by normal distribution, which is very common, which is common distribution for walking speed based on many studies. We designed model in 2 basic setups in Pathfinder, in latest version of Pathfinder. The first model setup is called basic calibration because we calibrated only input flow parameters, step function that I described, and walking speed parameters. And second model is called model B, advanced calibration, and we calibrated input flow parameters, walking speed parameters, but also waiting points and the distribution of waiting times. In the picture, you can see a basic scheme of waiting room, and red circles are waypoints produced by Pathfinder. You can see 2 entrances for center clients and 2 exits that clients used. About measurement region, I will talk about later. So results. Here you can see a simulation performed for Model B Advanced. You can see that agents enter the waiting room and some of them stops at waiting points locations. We used sample of 132 trajectories for validation tests 2 and 3, which I will describe later. This sample was chosen based on only one condition, and it was that those trajectories needed to start in front of measurement region and ended behind it, so that we have a sample of trajectories that we can compare behind model setups and video footage, between model setups and video footage. So first validation test is very basic. It's qualitative, just visual validation test of trajectory shapes produced by simulations and video footage. You can see that model A basic, which doesn't include any waiting points, produces very straight trajectories, which is, of course, as we expected, because agents do not have reasons to stop or change their directory. So this is kind of basic setup that we would use if we wouldn't have analysis of waiting points. Model B advanced trajectories are more similar to video footage. You can see it at first look. But in further research, we would like to have some quantitative analysis of this so we can compare bundles of trajectories between themselves, and we don't have to do this just by visual control or check. Validation test 2, we compared here time of passage through measurement region, which you saw on previous picture. Here we can see that data from video footage and data from Model B advanced are kind of similar from the point of view or central tendency and variance. And you can see that Model A basic data are comparable from the point of central tendency, but has very low variance because the agents didn't stop and didn't change their directory, so time of passage is very similar for each one of them. Validation test 3 showed that we need to improve some steps in our procedure and maybe go further in some research areas in this topic, because you can see that all three data sets are very different from each other. Model A basic data are has very low variance. Video footage has very high variance and different central tendency. And we argue that this has primarily three reasons. It's caused by three causes. One of them is that detector detected trajectories and produces some error because of distortion of camera lenses. So the trajectories from detected trajectories looked more curved than they really are because camera lenses produced distortion. So one of the steps that we have to do is to improve detection process and undistort these images that the camera produces. Second reason is that even if the person stood at its place, so his walking speed was approximately 0, the detector or trajectory length of this person increases because detector oscillated around the person. So these minor changes do not disqualify data to be used, but trajectory length increases in time. So at this graph, it can be very seen. And third reason is given by occlusion. Occlusion, by that I mean that if I walked behind the chair, for example, and camera would see me and chair between me, it would detect me correctly, but this chair can mean that my trajectory curve would be a little bit more curved than it should really be. So again, this false detection do not, in our point of view, disqualify data to be used, but at this graph, it looks like the trajectory, artificial trajectory produced by simulation is very shorter. So we need to find some level at trajectory produced by detection is real enough, and also trajectory produced by simulation is also real enough. So we are trying to find some line that suits for this task. So we believe that more sophisticated data collection methods are needed to calibrate ingress model to produce valid model outputs, because as we all know, validity of model outputs very correlates with validity of model inputs. And based on this starting research, we believe that this direction of our research is right way to continue with. And yeah, as I said, there are many things that we have to improve to make some more proper scientific results. So one of them is quantitative validation, test 1, as I said, geometry similarity of bundles of trajectories that we want to compare. So thank you for your attention, and if you have any questions, please ask.
It's a really interesting presentation. I was just thinking some of the comparisons between the paths sort of goes back to what Brian was saying earlier, right? And just establishing how similar one set of assumptions are to another. I also think, and better mathematicians than I in the room will correct me, but there's the functional analysis that's used in the verification protocols for modelling, where you can compare one curve with another and the distance between those curves. And I'm wondering if you could plot the paths into a Cartesian space, you could just compare the distance between paths. I guess the trick's going to be identifying what are the comparable paths, right?
Yeah, exactly. Yeah, that is further step. I know what you mean. I know the article that you refer to. And yeah, we use this article to compare like evacuation curves, but we didn't do it at trajectories, but it makes sense to try it. Yeah, it's just a curve. Yeah.
Okay. Hello, Pavel Hrbák from CTU in Prague. If I understand it correctly, that calculating the length of the path means like adding up all distances from frame to frame.
Yeah.
Okay, so there definitely will be some prolonging due to staying, etc. You might consider just avoiding this by doing some cubic spline approximation of the path or something like that, which should filter out those small steps, perhaps. Suggestion.
Yeah. Those trajectories that we got were already smoothed by B-splines, but there's a question for us, because when people walk, it is easily approximated by a B-spline, but when they're stand and they're at their place, the B-spline has kind of problems, because there are a lot of points at one place, I would say. So when there are trajectories length like 20 meters, 30 meters, and then there is a little bit changes in distances, I believe that B-spline can have some problems with that. So there need to be some thoughts and techniques to how to approximate it. But you are right, yeah, that we need to approximate those distances.